Hey everybody, so today we are going to go ahead and cover the question, how does adding branches lower resistance? And what I'm referring to there is, how do we lower the resistance when we add resisting elements to the circuit? So if I have, say, two light bulbs in series, and then I add another one in parallel to one of those bulbs, why does the total resistance of the circuit get smaller? And that is something that we have seen now in a couple of different activities, in a couple of them in Unit 3, but then especially recently in Unit 5, Activity 3 and 4. So we're going to go ahead and cover those today so that we can do the worksheet here today without as many issues. Here we go. So it's kind of a weird concept. We're adding more resistors, but we're getting a lower resistance. I do want to real quick define this term here, equivalent resistance. Equivalent resistance is another way to say the overall resistance, the combined resistance, or the total resistance of our circuit. Each individual bulb in itself has a resistance, but when we combine these bulbs either in series or in parallel, together they have an overall resistance or a combined resistance, or the term that you'll usually see used in most textbooks and by most engineers is equivalent resistance. So two bulbs or more bulbs in series or in parallel would have a combined or equivalent resistance. What we've seen is that when we add resistors in series, the equivalent resistance of our circuit increases, and logically that makes sense, more resistors, more resistance. But when we add resistors in parallel, the overall resistance appears to decrease, which seems to defy all common sense and logic. So we're going to go ahead and do a little treatment of why that is the case. Some important notes that I want you to keep in mind as I start to discuss this are first that each wire already has charge in it. Remember, the battery is not shooting charge out of it and putting charge in the wires, so the charge is already within those wires, and it's just getting driven around the loop by a difference in electric pressure in the wires. And that difference in pressure is established by the charge being compressed by putting more charge or positive charge into a wire, or the charge getting depleted, either by taking away that charge from that wire and making the pressure less. And that compression or depletion happens during the transient phase or the transient process in our circuit, which is something that we've been covering over the last few days as well. Remember, the transient process is just that phase before the circuit before really we see everything. It usually happens very quickly, where in that transient phase, the flow rate in and out of each wire might not be the same. And so if there's more charge coming into a wire than is going out of that wire, then that charge is going to build up inside that wire. And so we're going to have the pressure increase in a wire or decrease if there's more charge leaving than is coming in. Okay, so that's how that difference in pressure is established. What we're going to look at now then is we want to look at this circuit in its steady state. And that steady state is where, again, we have some charge here. You know, we've got like four little bits of charge that are moving. And the flow rate of charge is the same everywhere in the circuit. So that would be a steady state circuit where the flow rate is no longer changing and the flow rate is the same everywhere in that series. Now here I have for us a circuit with two identical bulbs in series. We'll just let them be two round bulbs, and those are two round bulbs in series with each other. And we have the charge moving through the circuit as these little dots. And as the four little dots of charge enter this bulb, four are also leaving that bulb and then going through the next bulb. We see that the flow rate, the number of dots or the amount of charge that's moving through each bulb is the same. So they do both have the same flow rate, and that's because they're in series. And since they're in series, they have the same resistance and the same flow rate. We see that they have the same pressure difference across them, whether that's red to yellow and then yellow to blue. Okay, so we can say that that's like red to yellow, and then yellow to blue, right? And we have that same pressure difference across both of those bulbs. Now what I want to do next then is to take that circuit and add a third identical bulb in parallel with the second. This is more or less similar to activity 3. When we did activity 3, we added a bulb in parallel with our middle bulb. Now what we're doing here really is we are giving this charge a second path or an alternative branch for it to flow through. So we're giving it another direction that it can go. We have these 4 dots here and it splits right into those 2 directions. So those 4 dots split into 2 groups of 2 to move through these 2 identical resistors. So what we see then is that when we added that additional branch, these 2 bulbs have half of the flow rate of the first. The charge from the trunk wire, that's this wire right here, the one that splits into 2 branches, the charge from that trunk wire splits, and we also see that the flow rate in both of those branches has to add up to the flow rate through the trunk wire. So we can't have a different amount of charge coming out of here as is going into here. That does have to stay the same, at least in our steady state circuit. Okay, so again, each branch has half of the flow rate of the trunk, but each branch has the same resistance as the trunk. Therefore, they must have half of the pressure difference. So if my pressure difference from the whole circuit, on the whole circuit, is red to blue again, right? If I've got blue here, and this pressure difference here is half of the, so the pressure difference from this wire here to this wire here, we want it to be half of the difference from here to over here. So what color must that one be? It can't be yellow again, because red to yellow and yellow to blue would be the same. If it's orange though, right, red to orange is a leap of 1, and orange to blue is a leap of 3. So it must be less than orange then, right? Because if it's orange, then this would be bigger than twice that jump. So it must be somewhere between yellow and orange. I'm just going to go ahead and color part of it yellow and part of it orange to show that it is somewhere in between those. Okay, it's somewhere in between those to make it so that this jump here is half of the jump from here to here. I'm sorry. Let's go back. That would make it yellow-green, wouldn't it? That would make it yellow-green. My bad. Yeah, that would make it yellow-green because this jump here is smaller than this jump there. Sorry about that. Unfortunately, the free version of the software that I'm using right now doesn't let me go back and edit that part out, but bear with me there. So this would have to be yellow-green in order to make this difference half of this difference. But again, the exact color doesn't really matter very much here because we're not really working with numbers, but I do want to make that clear. Okay. So if we view those 2 parallel resistors as a single combined resistor, or in terms of their equivalent resistance, since it has half of the pressure difference and half of the flow rate. That means that the equivalent resistance of these two bulbs in parallel must be half of the resistance of the one bulb by itself. And that is because this charge is given an extra path to flow through. It has twice the available path, and so it has the double the available path is going to be half of the total resistance. So that's why it has that sort of counterintuitive kind of feel to it, where adding that resistor actually decreases the resistance. It's because it makes that extra path available. Okay, in summary, the main point that you need to get from that is that two parallel resistors has the same effect on charge flow as a single resistor with half as much resistance. So adding another resistor in parallel decreases the total resistance of that section of the circuit. Okay, I suppose that that'll do for now. What you're supposed to do now is to pull up the worksheet that I've given you right below this video. So go ahead and complete that worksheet and have a good rest of your day. Talk to you again tomorrow. Bye.